we're going to look at the sample size, but this time to determine what is the appropriate sample size needed in order to achieve a goal as far as the margin of error. Ironically, the sample size is the first thing that a person needs to figure out. So this is really the first thing we should be doing, and we have left this for last. The sample size needs to cover a certain need. It should be large enough to make sure we can use the central limit theorem. Besides this, it also needs to satisfy the following requirements. The user gets to pick the needed margin of error. So even though we've calculated the margin of error before, really this is something that we determine ahead of time. This is the maximum margin of error. So really, what really the user is about to pick is maximum. We cannot have it any worse than this. So that's really what the user gets to pick. When we actually get the data, this might actually go down. The user also gets to pick the required confidence level. So again, this is user chosen. But as has been mentioned before, 95% is the most common thing you choose, followed by 99%. And once in a while, you'll see 90%, but not too often. Once those two are determined, we need to use that information to calculate the required sample size. Now, here is the margin of error formula. And so we get to pick the value. We'll say the margin of error can be no worse than, let's say, 0.03, for example. Now, once that's done, and we determine the confidence level, this allows us to figure out what n is. Now, notice that I've replaced p hat and p with p star. And why have I done this? Because in the formula that we're about to do, we also get to pick this value. The value p star is user chosen for this particular calculation. It is not derived of data, but it could be. Maybe a preliminary study. The big thing is that maybe there is some data and we could use that as an estimate. Maybe there's some p-hat value that exists, so we'll use that as an idea. Or maybe somebody has done this something similar and they have a range of values. They have the p-hat value, which of course sits in the middle, but there is like a lower bound and an upper bound. Maybe you would choose well, you'll see what you'll choose, but instead of choosing one of these, we'll choose one of the n's to achieve a certain goal, depending on the following. The value of p star, maybe your guess at what p is, or p-hat value from a similar study, or the value that produces the most variation, larger standard deviation. And that's really, when I mention these two endpoints, that's what I'm talking about, the largest possible variation, which happens when p is 0.5. So one thing to know that when p equals 0.5, this causes the most variation for, again, this calculation, SD of p-hat, or even, because we'll be using this for confidence intervals, SE of p-hat for the same sample size. Well, and really for any sample size. There's a curve associated for every single sample size. But this, again, causes the biggest change. So now what are we going to do? Let's do this and solve for n so we can use this formula to determine what the formula will be for sample size. So to do this, I'm going to divide both sides by z star. When I do that, again, ME is from margin of error. I'll just leave it as ME, sometimes you see with the dots. I'll divide both sides and I'll get this, z star. And this is equal to. So we're doing a little bit of algebra here. What I do next, where I want to get rid of these square roots because I want to solve for n. I'm going to square both sides. Let's show that. I'm going to square this side. I'm going to square the other side. And what you get is the following. Squaring this side will get rid of the square root. Now, I'm going to flip both, invert both fractions that you see right here. And really what I'm doing, just so you realize there's nothing hokey, If I say 1/2 is equal to, let's say, 4/8, you recognize that's true. 4 is a half of 8, or 1 is a half of 2. If I were to invert both of these, I would have 2 is over 1 and 8 is over 4. And again, notice I have the two sides remain equal to each other. So that's all I'm going to do. I am going to invert both, and both sides will still be equal to each other when I do this. So it's just an easier way to manipulate this expression. And there we have it. Now I want to solve for n, so I'll multiply both sides of this equation by this denominator. And what I get is the following. And there's my formula. This is formula to find required sample size. And note the following, always round up. Your derived sample size value to the nearest integer. So you're always going to round up. Remember, you're trying to find the largest value of n that will what? Limit the margin of error to be the maximum value. So notice again, we've mentioned this before, as n increases, right, as n goes up, what happens to the margin of error? It goes down. So when we choose, for example, let's say that n turned out to be 278.2. So what would n be? N would not be this. N then would be 279. You round up because at 278.2, you get exactly that margin of error. But you can have a 278.2. You can have a 0.2 of a sample. So then you just round up 279, and now that guarantees that my margin of error is protected. The one that I chose, my maximum I chose, is now protected. Of course, by going slightly above, the margin of error will be slightly smaller. So when you look at your formula sheet, notice this formula to find sample size is sitting right here. And notice this formula sheet also have the confidence levels that you need to determine an appropriate critical value here, the z-star. Look at this example. You have a 6-sided die, which you assume is fair. You will toss it several times to see if you can approximate the chance of die landing on 3 correctly. You will choose a margin of error of, okay, let's just pick one. Let's just say 3%. And a confidence level of, well, let's just go boring, 95%. And now, what's the p-star value? Well, I know it's a fair die, okay? So, and what I'm after is the chance of landing on 3, so I realize that the correct value for p is 1/6. So let's just choose that for the moment. I know what this is. So again, this will be my p-star value and see what happens. So let's say that I wanted to estimate this required sample size. So again, this is a little bit strange that you do know this value exactly. But who knows? Maybe the die is not fair, right? Maybe there's something wrong with it. But we're just doing this so we can see how the formula works. So what is the required sample size? So I'm going to go back to my formula. And it just says to do the following. Find z-star. Well, z-star is 95%, so 95%, 1.96. Got 1.96. The margin of error. Margin of error is 3%. So again, I cannot leave it in percentage form. 0.03. Then it says to square. Now find this p-star value, which is something I chose. Well, I chose 1/6. So this is 1/6, then the other one's 5/6. And we'll have this completely off camera, but I already calculated this. And when I calculated this, I came out to 592.83. So what's my sample size? Well, we always round up. So no matter what's here, we round up. So this sample size turns out to be 593 rounded up. So that's my required sample size. For the scenario that I concocted, which is I want margin of error 3%, I want this percentage confidence, and I'm going to choose 1/6. Like I mentioned before, and I want to point out to you, is that 0.5, p is equal to 0.5. Again, p-star is just, there's nothing magical about the star, it just means that I choose it. But I'm just talking about now in general. The population proportion, the probability of 0.5 contains the most variability. What would have happened if instead of choosing 1/6, I would have chosen 0.5? So I'm going to write everything down except this part is not, suppose I chose instead P star equal to 0.5. That means this is 0.5, and then the other one is again 1 minus that, so it's 0.5 again. Success, failure. What do I get here? When I do the calculation, I get 1067.11. If I then round up, I must always round up. So notice this time you go, oh, it shouldn't be 1067. No, no, no. No matter what, doesn't matter what the fraction part is, always round up. So in this case, n is 1068. So you'll notice we went from a sample of 593 to one that's 1068. And why is that? Because the variability, as P approaches 0 or 1, the variability goes down, right? If it's close to, like, say, if P is equal to 0.9, that means it happens most of the time. When you look at your data, it's mostly going to be success, 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 once an occasion of failure, which means there's not a lot of variability. And that's what's happening here. We don't need a big sample size here because our variability, this is about 16%, is close to 0. Okay, so at that point, there's not, you don't need a big sample size. But if we go to the 0.5, which is the most extreme case, that's some extreme, notice, is not going to 0 nor 1 for variability. The most extreme value happens at 0.5. This causes the most variability. And now you can see that to overcome all that variability, you need a bigger sample size, because that's what this formula tells you. Standard error, if you want to bring standard error down, or the entire thing, the margin of error, n needs to go up, and that's what's happened. All of a sudden, these two values can control how much variability there is as well. The closer this value is to 0 or 1, the less variability. The closer this value is to 0.5, the most variability occurs, regardless of sample size. So once we chose that, then now for that to get it down to a margin of error of 3%, which 1.9 with 95% confidence, that's the required sample size. Let's do another one. All national polls, the ones that, are you happy with US Congress or whatever it is, meet at the 95% confidence level with a margin of error of 3%. Calculate P star equals to 0.5. How big of a sample do you need? Well, we just did it, right? If I did that, then it'll be 1.96, again, 0.03 squared, 0.5, 0.5, and that will give you, again, 1067.11, 1068. All right, so what was the purpose of doing that? I mean, it's really the same question as this. So the one thing that we're trying to do here is just we're trying to estimate a chance of a die landing on 3 correctly. Here, we're doing a national poll, so the entire nation. And they're talking about Congress. You notice, regardless of the situation, the sample size is exactly the same. So the question becomes, is the sample size dependent on population size? And the answer is no. An emphatic no. Sample size, population size is irrelevant when it comes to determining sample size for what we're doing at the moment. Okay, so there's a lot of rules, like that. There's a 10% rule, but that has to do with when we're sampling with or without replacement. But for this scenario, what we're concocting, because really what we're doing is trying to get accuracy at some margin of error for some confidence level. So the population is irrelevant when it comes to determining sample size for this purpose. What is irrelevant? What is relevant is measurement variability. I want to bring your attention to something else. So what do you mean by measure variability? Well, the standard error measures the variability of p-hat. So if I go to standard error, it means I don't have the actual value. I just don't, it's an approximation. The real value is right here, which is standard deviation. So the standard deviation measures the variability of my statistic, this one right here. And as n goes up, so does the variability. But what does the population variability have to do with anything? Well, if I were to use this formula, notice what do I mean by population variability? That means just sampling once. If I turn this into a 1, then the population for this measurement variability is just going to be changes to a 1. So then all I have is this. The population variability is measured by these two. When n is 1, I'm measuring 1. And again, that means that this value, this output, that's a population variability, it changes depending on how close p is to 0 or p is to 1. When p is 0.5, this is at its maximum level. Here is something we'll do later, and it's a confidence interval, but for the means. And again, notice we have something similar. Here's the standard deviation of the population. And again, notice that what does this formula tell you? You can see it a little better here. Because instead of having a formula for standard deviation, we just tell you, well, here's what it is. But now you can see that this is the population variation. And really, when I'm determining something for the confidence interval, this is the thing that matters. How much variability is in the population? Nowhere here is there any mention of population size. And here's the confidence interval for means. And again, notice this formula sitting right here. There's nothing here there's nothing concerning population size. So there's nothing here about concerning population size. What is relevant is population variation. That's what's important here. So keep that in mind. What occurs when the standard deviation of the sample distribution, when we quadruple the sample size? Well, let's just do this real fast. I'm going to do this algebraically, but you can do it non-algebraically. Here's all we're saying. Here's your, and we can knock this out. And this is the standard deviation. I'm going to just use the margin of error. Same idea. The standard deviation is just this part. And right now I'm using this margin of error. And the standard error here. But this is some value. And what is it I want to do? Well, let's say that I want to cut this in half. So what I want to do now is, what happens if I decide to do the following? Cut this value in half, which means cut this other half value in half. How does that affect the sample size? Well, I'm going to do a little bit of algebra here. So notice now, whatever this value was, I cut it in half by multiplying by a half. But how does that affect n? So I'm going to just move it over, and I'm going to do the following. You would agree that square root of 4 is 2. So all I'm doing is moving this over here and put it under a square root. And I don't know if you remember a few rules of roots, but as long as two things are under the square root, let's say that I'm multiplying them together, I can just write them under one root and multiply them. So this says square root of a times square root of b. So if that's the case, that's equivalent to saying square root of a times b. And that's what I'm about to do. This is square root. I'm going to put it right underneath. I'm multiplying them. Boom, let's put them inside. And when I do that, notice this a was under the square root. Let's say that I went underneath next to the square root, that this square root is now taken care of by this larger one. So now what I have is 4n. And there we go. There's my new sample size. So if you had some value, say we put values here and we came with a margin of error, and you say, I want to take this margin of error, but cut it in half. What is it that would have to happen to the sample? And the answer is, here it is, cut in half. As far as the sample size, you have to quadruple it. So to reduce variability, again, could be the margin of error as a measure of variability. Sorry, spelled here. To half its previous value, you must quadruple sample size. And again, we use this in the formula, even for means. Here's the standard deviation. For means, if I want to cut this variable, the variable for the standard deviation of the means, what do I have to do? Well, I can just come over here, set this as some particular value, and I want to cut this in half. So here's what it was before. Notice I want to cut this in half, so now I want this output to be half of what it used to be. And I claim that it's just going to be, well, quadruple the sample size. So right now, what it was before, let's call this N1. So now instead of doing N1, I'm going to do 4 times N1. And now I'm going to use that rule backwards, square root of 4, square root of N. I can separate them. Square root, and again, I'm going to have, well, I'll go to 2 steps. So now I have square root of 4 times square root of N. But what does that value mean? Square root of 4 is 2. And there we go. I have halved this value, just like I mentioned I would. It is now half of what it used to be. So keep that in mind. To reduce your variability in half, you must quadruple your sample size for these situations.